All right. Good morning again to everybody. We have a webinar today on life cycle greenhouse gas emissions of both internal combustion and electric drive cars and two-wheelers in India. We're simultaneously later today doing another webinar that's focused more on European assumptions. This is a study that my colleague Georg worked on over the last year, and it got released a couple of months ago. Just a couple of housekeeping announcements. We will be recording this webinar, so please be aware of that. All the slides will be posted on the website as well, so you don't have to worry about that part. Once Georg is done with his presentation, we will open it up for Q&A. I think we've got a small group here today, so we should be able to unmute everybody who wants to ask a question and do that. But if you do have a question while Georg is still presenting, you can use both either the chat pane or you can use the questions pane on your GoToWebinar control panel and type in your questions in either place, and we'll make sure that those get addressed at that time. If something can be easily explained away, I will just type in the answer there. But if not, we will pose that question to Georg after his presentation is over. So with that, let me turn it over to Georg and take it away.
Yeah, good morning, everybody. I hope you can hear me well. I'm very happy to present some results to you today. Yeah, like Anup said, on the life cycle greenhouse gas emissions of passenger cars and two-wheelers in India. And my presentation will follow this structure. So first introduce you into the topic, then show you some methodology, and then the key results and key messages floating from it. So for the introduction, yeah, you can see on this slide the reduction in greenhouse gas emissions of transportation globally that is required to keep global warming below 1.5 degrees C. And that's from a study we conducted last year. So we need to reduce the greenhouse gas emissions from transport by about 80% in 2050 compared to today's level. And we need to reduce these amount of emissions while still the global car fleet and HGV fleet and aviation and also maritime transport keeps to increase. So the demand will increase, but still we need to reduce by about 80%. And the aim of this study is to show which technologies, or to understand which technologies are able to deliver that reduction in greenhouse gas emissions, even though we will see an increase in demand in transportation. And I will show you some 4 key points on the methodology. But before I explain you a bit the scope of the study. So this study is on life cycle greenhouse gas emissions, and the greenhouse gas emissions covered here are CO2, methane, and nitrous oxide. And the life cycle means that we consider the vehicle cycle, so all the emissions from the vehicle and battery production, including also the raw material processing and extraction. And then the emissions during the maintenance of the vehicle, and then in the end also the emissions, all the emission benefits of recycling at the end of life of the vehicles. That's for the vehicles, and that's one part. The other part is the fuel cycle, the well-to-wheel analysis, and here we consider the greenhouse gas emissions of the fuel and electricity production, but also the indirect land use change emissions from biofuel productions, and finally the emissions of the combustion of the fuel in the vehicles. And for the methodology, starting with this slide, I hope that the delay is not too strong. Here our study differs methodologically from other studies. We do not assume the constant electricity mix, for instance, for the whole lifetime of the vehicles, but we cover the improvement of the electricity mix over the lifetime of the vehicles. So you can see on the right that for a vehicle lifetime of 15 years, cars registered in this year will run until 2035 and will experience an increasingly greener electricity mix. And you can see on the right here that there are, for India in green, 2 scenarios. One is like a worst case scenario, which is the stated policy scenario. So here we only consider the improvement of the electricity mix that can be foreseen from policies already in place. And then you see, this is the higher line, and then see the lower line, the dotted line, which is the best case scenario. And here we consider the improvement of the electricity mix that would result from a policy that would be aligned with the Paris Agreement of limiting global warming to 1.5 degrees C. So these are the best case and the worst case scenario, and we always show a range of values corresponding to these best case and worst case scenario. And we do the same for the biofuel and biogas blend. Also here, we consider the improvement of the average blend of biofuels and biogas in India. And that brings me to the second point. When it comes to biofuels, it's important not to only look at the emissions of producing these fuels, so the direct emission of producing these fuels. It's also important to look at the indirect land use change emissions. And you can see for ethanol on the left and biodiesel on the right, that especially for biodiesel, for some pathways like palm oil-based biodiesel, for instance, you can see that with this additional indirect land use change emissions, the emissions can actually be higher than for fossil diesel. And for ethanol, you are usually below the carbon intensity of fossil gasoline, but still you see that there's a big difference between ethanol based on corn, for instance, which has only a moderate reduction in greenhouse gas emissions, compared to ethanol pathways that are based on energy crops on one side, or on residues and wastes, and these have much larger reduction in greenhouse gas emissions, because for these residues and waste and byproducts you have less or no land use change emissions. And for India, and for the future mix in India, we considered the improvement of the average gasoline and diesel blend according to the 2018 version of the National Policy on Biofuels. And in that version, the policy was focused on non-food-based biofuels. I'm not an expert on this, but I heard that there was some changes lately. Maybe we can discuss this later. But here we still consider the 2018 version. So we have for India assumed high shares of sustainable biofuels. The third point is the battery production, and here our data is lower than in comparable earlier studies, because we use the most recent data, which is based on industrial scale battery production, instead of estimations that are only based on pilot plants on battery scale production. And here, with these numbers that really are based on industrial scale battery production, we can see that if you produce an NMC 622 graphite battery cell in Europe, you would have like 54 kilograms CO2 per kilowatt hour. In China would be 69 kilograms CO2 per kilowatt hour. And we consider that for India, it would be 68 kilogram CO2 equivalent per kilowatt hour for the production emissions. And this is significantly lower than earlier studies used. The last point on the methodology is that we consider first methane leakage from natural gas and natural gas-based hydrogen pathways, which are blue and also green, blue and gray hydrogen. And here we consider that methane generally has 30 times higher global warming potential than CO2 when you account for a 100-year time frame. But when you only look at the short-term 20-year time frame, the global warming potential of methane compared to CO2 is even higher, 3 times higher than for the 100-year lifetime time frame, and here it's like 85 times higher than CO2. So even small emissions of methane have a big impact here. So therefore, it's very important to look at the methane leakage emissions. So now coming to the results. On this slide, you can see an overview of the 4 regions we assessed in this study. So that was Europe, the United States, China, and India. And you can see a comparison of the life cycle greenhouse gas emissions for medium-sized passenger cars driven on gasoline or on the gasoline ethanol average blend and BEVs powered by the average electricity mix. And you can see this for cars registered this year and for cars registered in 10 years in 2030. And you can see that in all 4 regions, we see a benefit of battery electric vehicles in their life cycle greenhouse gas emissions already today. And this improves for future cars. Now let me start with a India-specific presentation. Here on the slide, you see the greenhouse gas emissions for sedan segment cars, average sedan segment cars registered this year for the individual powertrain types. And from left to right, you can see gasoline, diesel, and natural gas cars. And you can see that diesel and natural gas cars do not really show an emission of greenhouse gas emissions on a life cycle basis when compared to gasoline cars. Let me already note here that gasoline cars include hybrid electric vehicles, so that's all kind of gasoline cars considered here. And then for the battery electric vehicles, you can see that already for cars registered this year, we can have 19 to 34% lower greenhouse gas emissions over their lifetime. And this is what I mentioned before. We have a range of values here because of this best case and worst case electricity mix scenarios. And when you consider a purely renewable electricity powered BEV, you would have a reduction of 79%. When it comes to hydrogen powered fuel cell electric vehicles, it really depends on the kind of hydrogen you use. So you can use coal hydrogen or natural gas-based hydrogen. You can use natural gas-based hydrogen combined with CCS. You can use hydrogen produced from renewable electricity. Here I showed like the 2 main pathways, which is hydrogen produced from natural gas, which is called gray hydrogen, and hydrogen produced from renewable electricity. And you can see that for hydrogen produced from natural gas, also because of the methane emissions, you do not really have a greenhouse gas emission benefit over today's gasoline cars. So fuel cell electric vehicles run by natural gas derived hydrogen do not offer a greenhouse gas emission reduction. If you use hydrogen from renewable electricity, in contrast, you can see a large reduction similar to battery electric vehicles powered only by renewable electricity. You have 68% reduction. This slide shows the results on cars in the SUV segment, and you can basically see that the trends are the same as for the sedan segment. And here's a slide on hybrid electric vehicles. So we didn't have the data for India to look into the average HEVs compared to average conventional gasoline cars, but we did that for Europe. And here you can see on the left the results for the lower medium segment, which is comparable to the sedan segment, and the SUV segment. And you can see that due to 23 to 27% lower fuel consumption, there's also a greenhouse gas emission benefit, which is 20 to 23%. So that might be surprising to some of you because hybrid electric vehicles usually show a higher reduction in fuel consumption on the paper, but in real world driving we found that the difference between the real world usage, fuel consumption, and the official test values is higher for HEVs, and that reduces the benefit a bit. But still, we can see a significant benefit. It's like 20 to 23% lower compared to conventional gasoline cars. And when we look into the future and we project how cars will look like in 2030, we see that for gasoline cars, the life cycle greenhouse gas emissions are lower than the numbers we had before. This is mainly due to the increasing share of sustainable, we assume this is only sustainable ethanol in the average gasoline blend. And you can also see that for diesel and natural gas, you have lower greenhouse gas emissions than for cars just today. But at the same time, that you can see that the reductions are not that high actually. So we have 10%, 20% lower emissions, but not a large scale reduction. This is different for battery electric vehicles. Here you see that for cars registered in 2030, we have 30 to 56% lower greenhouse gas emissions, which is an improvement. But you can also see that the range of uncertainty got bigger because the more we will look into the future, the harder to see like how the electricity mix will look like. So the truth will lie somewhere in between, we expect. And for natural gas and green electricity derived hydrogen, you see more or less unchanged figures here because these are just the pure pathways and not mixtures presented. So the renewable electricity-based pathways, so for battery electric vehicles and also for fuel cell electric vehicles, are the ones we need to look at when looking at the far future. So I started with a slide showing that by 2050 we want to have an 80% reduction of the greenhouse gas emissions, and we can see that these two powertrain types deliver that large-scale reduction, whereas the other powertrain types do not deliver that reduction. But I want to compare the two of them a bit more in the next slide. And this next slide is about the energy consumption or the energy demand of these pathways. And here you see that when you produce green hydrogen from electricity, you have some inefficiency in this electrolysis process, but then you also need to compress and also transport the hydrogen, and then in the end you put it in the car and you need to re-electrify it, and also there in the fuel cell you have some energy losses. And taken all together, the energy losses from hydrogen production, from transport and processing, and then finally the energy losses in the car from the fuel cell, you need 3 times more of the same electricity compared to battery electric vehicles. So in a world where we are limited with renewable electricity, it's important to consider this difference in energy intensity. And then on the very, very right, you can see like a worst case scenario for this, which is the use of e-fuels. So e-fuels are produced from renewable electricity-based hydrogen and CO2 taken from the air. And this production process is very energy intensive. And then when you combust these fuels in the car, you have a very low efficiency compared to electric powertrains. And therefore you would need in the end 6 times more energy to drive the same distance with a similar car compared to electric vehicles. And because of that high energy demand, e-fuels are very expensive to produce. We expect that they will cost €3 per diesel equivalent still in 2040 and 2050. And with these assumptions, we consider them to have very low impact on the average fuel mix. They would just be too expensive to produce, especially for the use in cars. That might be different for aviation. So here, e-fuels can play a role for sure. But for passenger cars, when you just compare these energy efficiency and consider that we're limited with renewable electricity, that's a big point to consider. Yeah, and here's a slide on motorcycles and scooters. Yeah, you basically can see that all the results we see for passenger cars are also true for two-wheelers. So also here, as we can see on the left, for two-wheelers registered this year, we have a significantly lower greenhouse gas emissions for electric motorcycles and electric scooter compared to combustion engine versions. And when you look into the future for scooters and motorcycles registered in 2030, you can see that this benefit increases. But you can also see that there's a slight improvement of the gasoline versions because of the higher share of sustainable ethanol we assumed. Yeah, this leads me to the key messages. And this is, yeah, first of all, that we found that for all 4 regions, including China, India, Europe, and the US, battery electric vehicles show the lowest life cycle greenhouse gas emissions when you consider their whole lifetime and not only look at the first year. Then we also see that when looking in the far future, only battery electric vehicles and hydrogen fuel cell electric vehicles have the potential to be near zero carbon, also on a life cycle basis. And we also see that there's no realistic pathway to decarbonize combustion engine vehicles. So for e-fuels, I explained that quite detailed, that they are too expensive and therefore projected to be too limited, but also are very inefficient to produce. And yeah, the same or a similar thing is true for sustainable biofuels. So these are, the more you want to produce them, they are expensive, and also here we have a limited availability. There's only so much you can produce them sustainably. It's easy to scale up like corn-based ethanol production, but this kind of ethanol does not provide large greenhouse gas emissions on a life cycle basis. You need to focus on sustainable biofuels, and here the supply is limited. Yeah, and the result from this is that if you want to reduce greenhouse gas emissions on a global scale from road transport, from transport by 80% in 2050 in order to limit global warming to 1.5 degrees C, we need the global passenger car fleet to be electric by a large extent by 2050. And for India, this means that when there's a vehicle lifetime of 15 years, most of these cars need to be electric by 2050. We need to start producing and selling new combustion engine cars in the 2035 to 2040 timeframe. So starting from that, there should be no new combustion engine cars on the streets anymore. The same is true for two-wheelers. So here it's even easier to electrify, and therefore we should start doing this earlier. And here there should be no new two-wheelers powered by gasoline on the road starting from 2035. And to approach that goal and to continuously increase the share of electric two-wheelers, fuel consumption standards are a very good way to go. And that's it from my side.